Hello, beautiful people. Welcome back to the lecture today. So today we're gonna go through one example configuration of the oscillator called PhaseShift Oscillator. So as the name suggested, this oscillator basically leverage a phase shift of RC network to sustain the oscillation. So first we started with this three-stage circuit in here. As you see, this is basically this phase shift oscillator is constructed of op-amp, operational amplifier. So we have three op-amp in here. So also first you have at the end, or I would say at the center of this phase shift oscillator, is your basic amplifier, right? The basic amplifier in this case is actually an inverting or inverter amplifier. Okay, just go back to your op-amp. You go back to your op-amp in electronics 1. You can see this. The next part of it is, so if you remember the construction of an oscillator or a positive feedback network is very similar to a negative feedback network. You have a basic amplifier in a feedback loop with a feedback network. So this is our frequency sensitive feedback network, and I'm going to call it beta. In this beta, we also have one op-amp and another op-amp in here, and this op-amp configuration is called buffer amplifier, or you can call it voltage follower. The reason, the way to notice buffer amplifier or voltage follower is when you see the negative sign is directly connected to the output side, okay, without any resistor. So the function of a voltage follower is basically, it's just want to make sure that the voltage here got transferred into here correctly, and this actually ensures that all of the loading effect between each RC network will be eliminated. Okay, and finally we actually have three RC network or three RC stage. This is the first one, this RC is the second one, and this is the third one. Okay, so this amplifier here, this basic amplifier or the inverting amplifier, will introduce the first negative 80-degree phase shift into the system. Your buffer amplifier eliminates the loading effect, and your RC network, the three RC network here. So each RC network have to provide. So since this one introduced negative 180 degree, right? And you have a three-stage RC. So each RC network must provide a 60-degree phase shift to introduce enough 180 degree counter to this for the frequency sensitive feedback network to produce a positive feedback. So just a food for thought, in this configuration we have three RC network. What happens if we have four RC network? What number will we have here? Finally, you may say, okay, this RC and this RC looks identical, but this one looks a little bit different. Luckily, this basic amplifier or this op-amp is at virtual ground, so this bus is grounded. So that leads to the third RC network, which is this one, would function just like the other two, this and this. therefore, we have the first requirement saying, okay, since all of C and R are the same, right? All of them must go by equally 60 degrees. And this third one function similar to the other two. So we know that on the RC network are assumed to be identical. So next I want you to derive a transfer function for each RC network. So starting with the transfer function for the first RC network. So I'm just going to skip through all of the magic derivation or magic rearrangement. We're going to have the transfer function of Vi over V1 over Vi, which is voltage at this point right here, over this voltage is going to be equal to S RC over 1 plus SRC. Okay, since the all RC network are identical, you can apply this transfer function similarly for this network. And you can have V2 equal to SRC over 1 plus SRC V1. And you can also apply for this network. So you can have V3 equal to SRC over 1 plus SRC V2. Okay. So now you can actually compare between R3, V3 and Vi, right? So now you can actually have a total transfer function for your whole, frequency sensitive feedback network beta. Okay, I got that correctly. So now you have that term in here, beta S. How about your open loop gain? So the open loop gain transfer function is going to be quite simple because now we neglect the frequency response of each op-amp, and this is basically just a single op-amp. We're going to have VO over V3 equal to negative R2 over R. This negative side introduce the negative 180 degree phase shift. So the magnitude of this gain will be R2 over R. So now we have the loop gain is going to be TS equal open loop gains multiplied by beta, right? So we have this term, come over here, only take the magnitude. We have this. So in order for the output to oscillate, we need two conditions. The first thing is this magnitude of loop gain have to be 1, and secondly the phase of this loop gain have to be at negative 180 degree. So if you plug in all of the number and you're trying to figure out at which frequency that makes these two conditions are met, you can calculate your omega naught, which is called the oscillation frequency, to be 1 over square root of 3 RC. And if you plug this omega back in here, you can have it to be, what do I say? You can have the loop gain to be negative R2 over R multiplied by 1 over 8. So this 1 over 8 factor here implies that if the magnitude of the inverting amplifier gain is larger than 8, the circuit will spontaneously begin to oscillate and will sustain this oscillation. So now we try to consider the transfer function of each RC network. So if we look into it, the transfer function is this, right? We can replace that with j omega. And if we replace with j omega, we have this function. Now we can plug in the exact value for omega naught. So we know that omega naught is 1 over square root of 3 RC. So you plug in that number in here. You can simplify it to this. Now this is a complex number, so I want you to break it down into magnitude and phase. So you can have magnitude is 1 over square root of 3 plus 1, this. And the phase is, so you have the first phase of the numerator is 90 degree, it's just only J. The second phase is, and the denominator will be inverse tan of inverse tan of 1 over square root of 3 b over a. So this is quite easy. You add 3 to 1, so it's 4, so it becomes 1/2. You put it here. For the phase, you just have to basically convert this group into subtraction. Okay, so let 90 minus inverse tan of 1 over square root of 3. 1 over square root of 3 equal to 30 degree. So you simplify that into a magnitude of half and a phase of 60 degree. So this transfer function proves that each RC network introduces 60 degree of phase shift. But it also shows you that 1/2 terms in here. So each RC network also introduces an attenuation factor of 1/2. Then the amplifier have to compensate for this in order to have the oscillation happen. So what happens if we get rid of one of the voltage follower? So the obvious thing is that the loading effect on of each successive RC network need to be taken into account during the analysis. But let's make our job simple today. So just for your checkup convenience, not deriving all of that, I'll give you the oscillation frequency. If you do it, you can derive a different oscillation frequency of square root of 6, 1 over square root of 6 RC. And also, in order to sustain the oscillation, the amplifier resistor ratio must be R2 over R equal to 29. So that's it for the phase shift oscillator. I mean, there's a lot of way and different method to implement this. I may reference, if you are interested, I may reference some of the notes I found from Texas Instruments. They have some wonderful notes how to implement in practice oscillator using an actual like TI chip or TI op-amp. But in the next lecture, I will cover the Wien bridge oscillator. So I hope you guys all learned something new today, and I will see you guys next time. Bye.